Okay, so we're on problem 4 from this section, and this lottery problem, it's a little bit vague because we're not quite sure whether we're choosing three numbers with or without replacement. It doesn't really say. Okay, so I'm going to assume that when we select 3 out of 10 numbers, we're going to select without replacement. Okay, the reason for that is without replacement means you can't pick the same number twice. You cannot pick the same number twice. It's used up, right? You're not replacing it. So you can't pick the same number twice or more. Okay, we use it up. We're not replacing it. The reason for this assumption is if we don't assume that, if we assume that it's with replacement, then it's way too easy of a problem because there's 10 ways to choose the first number. Then there would be 10 ways to choose the second number, and then 10 ways to choose the third number. So the total number of choices would be 10 times 10 times 10, or 1,000. And you'd have one winning combination, so you'd have a probability of 1 out of 1,000. So that's too simple of a scenario. So I'm pretty sure what they mean here is that we're selecting without replacement. Okay, we're not picking the same number twice. So the next thing to think about is what constitutes sort of the set of outcomes that we're going to select the winner from. So we want to sort of identify the set of outcomes that we're going to choose from. And so selecting 3 numbers out of 10 numbers without replacement, this generates my outcomes. Okay, so my outcomes that I'm going to choose from, and that's typically in these sorts of application problems, you want to identify all your outcomes first, and then from those, we're going to select which ones are declared to be the winning outcomes. But first, let's generate all the outcomes. So basically, I want to select 3 numbers out of 10 without replacement. Okay. So without replacement means, remember, without replacement means we're going to use either permutations or combinations. We're not going to use just simply multiplying 10 times 10 times 10. Okay, 10 times 10 times 10 would be with replacement, where you could use a number over again. Okay, we're not assuming that. The next question is, can we assume that does the order matter or not? So, in other words, what does a particular outcome look like? So a sample outcome would look like this. Sample outcome would just be 3 numbers that you've chosen. Okay, I'll call this N1 for number 1, number 2, the number 3. Here's your 3 numbers. Put them in the boxes. Okay, there's a sample outcome. We're going to assume, again, no replacement, so without replacement. And we're also going to assume, what about the order? Does it say that your first number has to match the lottery's first number, and your second number has to match their second, and your third has to match their third? Or does it say that if your collection of numbers matches their collection of numbers, you win? And I think that's what they mean. If your collection of numbers matches their collection of numbers, you win. That means that the order is not important. It doesn't matter which number you pick first, second, or third. It just matters what numbers you pick. Okay? So we're going to assume the order does not matter. The order is not important. You just want to have the correct numbers chosen in your particular 3-number outcome to win. You just have to have the right 3 numbers. It doesn't have to be in a certain order. Okay, so these are the assumptions we're going to make. No replacement, order not important. So therefore, you should be able to generate the number of possible outcomes using either combinations or permutations. Okay, it's either going to be a permutation or a combination. I'm not going to tell you which one. You should be able to generate that. Okay, and you should be able to figure out the numbers involved, right? Because we're picking 3 things out of 10 things. All right, so that should be pretty easy. So this generates this generates the number of possible outcomes you could get. Okay, that's sort of my first step in a problem like this. My next step is to single out or identify the winners, the ones we're interested in. Identify the special outcomes. What do I mean by special outcomes? The ones that are classified as being the event we're interested in this case, the winning lottery number in this case. Okay. And there's in each of these kinds of problems, you're going to have certain outcomes are singled out as special. That's the event we're looking for. So the event we're looking for is that you have a winning lottery number. So of all of the different, you're going to have like hundreds or thousands of possible outcomes when you do your computation here. How many of those are winners? Well, how many numbers did the lottery company draw? Like how many 3-number combinations did the lottery company pick when they ran this round of the lottery? Well, how many 3-number combinations, like how many combinations does a lottery company always pick? They just pick one. Okay, there's one winner. There's one winning combo. Okay, in this case. So the special outcome, the number of special outcomes in this is just going to be one. There's one winning combo. Of all of those hundreds or thousands of possible outcomes that we could have chosen, only one of them is going to match the lottery choice, and so only one of them is going to be a winner. Okay, and now step 3, I'm kind of running out of room here. I guess I'll sneak step 3 in up here if you're okay with that, is the probability of the event, which is choose the winning combo, is equal to what? The number of ways the event can happen, number of ways or number of outcomes for the event, divided by the number of ways for anything, for all outcomes. Okay, well, the number of ways for the event of picking the winning lottery combination is, well, how many winning lottery combinations are there? We're assuming the lottery is only picking one winning combo. And over here, this is either going to be a permutation or a combination. I'm not going to tell you which one. You need to figure that out based on the choices we made here. Okay, based on our analysis. Okay, so there's one special outcome called the winning outcome, and out of a whole bunch of possible outcomes that you're going to compute. Okay, and that's your probability of winning. Okay, number of ways the event can happen divided by the number of ways anything can happen. Okay, that's it. Not too bad, right? Maybe just one bad? See, math joke. No, not too bad. So it's one bad. No, boy, that's like 5 bad, right? That joke. Okay, let's go on. Okay, so here is problem number 5. And again, we're going to make the assumption that when we select 5 numbers out of 45 numbers, that the selection is done without replacement. Okay, so typically on these sorts of problems, you want to identify the set of outcomes that we're going to be working with. So we want to identify or sort of figure out the structure of the set of outcomes possible. Okay, so what does the set of possible outcomes look like? What's a typical outcome going to look like? It's going to look like 5 numbers, right? Number 1, your number choice number 2, your number choice number 3, your number choice number 4. And again, these are little boxes that we're putting our numbers into. Okay, so we're going to put 5 numbers into these boxes. Now, we're assuming again that this is without replacement, meaning you cannot pick the same number twice. It's used up. You're not replacing it. Okay, once you choose it, it's gone. All right, so that is going to change how we analyze things. Also, what do they want to happen? They want 3 of the 5 numbers to be winners. Okay, to match the winning numbers. The other 2, and this is kind of a weird lottery because when you pick 5 numbers, if 3 of your numbers match the winning numbers, you win. Okay, exactly 3. So it says exactly 3 of your 5 numbers have to match the winning numbers. So that's going to help me pick, which of these possible outcomes is a winning outcome. But before we do that, how many are there? Okay, what's the number of possible outcomes that we're selecting from? Well, that's going to be either a permutation or a combination. Okay, it's not going to simply be 45 times 45. Each initially you have 45 numbers to choose from. Why can't I just do 45? I have 45 choices here, 45 here, 45. Why can't I just do 45 times 45 times 45 times 45 times 45? That would assume you're replacing the number and you could use the number again. Okay, we're assuming that you're not doing that. Okay? So once you're not doing that, once you're not replacing, then the amount available goes down each time, and then you're dealing with permutations or combinations. Okay? And one of them is the difference between permutations and combinations is in one case the order matters, in the other case the order does not. Okay? And you have to know which one's which. Now, once you identify which one's which, which one we need here, then you should be able to get your possible outcomes. Remember, we're selecting 5 numbers out of 45 numbers. The question is it combinations or permutations? So to help you make that decision, let's think about it. Are they saying that your first number has to match the first winning number, and your second number has to match the second winning number, and your third has to match the third? In other words, are they saying that your numbers have to match in sequence, in the same sequence as the winners, or they're just in general, your collection of numbers has to have the numbers in it that match the winners? And that's really what they're saying. Okay? They're saying that your collection of numbers has to match the winning collection, or at least 3 of your numbers do. And so the order does not matter here. Okay? So that should help you pick which of the computations to use, permutations or combinations. Now this is going to be the denominator of the probability. Okay? Because the probability of an event, remember, just to kind of review real fast again, probability of an event E is equal to what? The number of ways for E to occur or another way to say that is the number of outcomes that give you event E divided by the number of ways anything can occur, any outcome can occur. Okay, which in essence is the number of total possible outcomes. Okay, so when you figure out the number of possible outcomes here, when you do this computation, you're generating the denominator of your probability expression. Okay? The denominator is the total number of ways anything can happen, all possible outcomes. Outcomes in this case are a choice of 5 different numbers out of a possible 45 numbers with no replacement, meaning you cannot just multiply 45, 45, 45, 45, 45, because you're not replacing things, and also with the order not mattering. Okay, so that should help you choose between permutations and combinations. So that's your denominator. Now, the second step is to identify the special set of outcomes that constitute the event that we're looking for. Identify the special outcomes that give us our event. Now, what event E are we looking for here? The event E is 3 numbers match the winning numbers. Okay, sorry, it's hard to write the bottom of the screen, the winning numbers. I know it doesn't look like the bottom of the screen, but I have weird software here. Okay, so now 3 numbers match the winning numbers, but what about the other 2 numbers? Okay, can they be anything? So let's say that I got a winner, and a winner. Okay, can I choose anything here for the other 2? What if by chance I get another winner there, like another winning match? Then I lose. Why? Because now I've got 4 winning numbers, and we don't want that. This is a weird lottery. They want exactly 3 of your 5 numbers have to match. Not 4 and not 5 of them. So we have to be careful here, because if you get winner, 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 you can't accidentally choose another winner, because then you lose. Because then it's more than 3 winning numbers. So this has to be loser, loser. Okay? So you have to choose 3 winners and 2 losers. So the special outcomes, 3 numbers match the winning numbers, and 2 numbers match the losing numbers. That says match, sorry. The losing numbers. Both have to happen in order to have exactly 3 winning numbers. You have to have 3 winners, and then the other 2 gotta be losers. You can't just let those randomly be chosen, because you might accidentally pick a winner again. Okay? So how do you make that happen? So that's going to be your numerator. Whatever we get here, whatever result we get here, the number of ways for this to happen, that is how many ways the event can occur. So that's my numerator of my probability expression. Okay, that's my numerator. Now, how many ways can this occur? Let's figure this out. So I need to get think about what we're doing here. We have to get 3 winners. Three winning numbers have to be chosen. In other words, 3 winning numbers out of the 5 in my outcome. And when we say outcome, we should be a little careful here. Think of it, a better way to describe it is this way. This is a weird problem, not crazy about it, but let's think about what the lottery is doing. The lottery has 45 numbers to play with, right? They're picking 5 of them. It's not quite clear from the description who's picking the 5. Are you picking the 5? Is the lottery picking the 5? Are both of you guys picking the 5? And it looks like we're both picking 5. Okay, they're picking 5 numbers, we pick 5 numbers, but in our case, we want 3 of our 5 numbers to match one of their winning guys, and the other 2 to match losing guys. It's kind of a weird problem, not crazy about it. It's hard to kind of parse it out. So the 45 numbers, it looks like what the lottery is doing is they're picking 5 of them, and they're calling them winning numbers. Which are the winning numbers? The ones they pick. Okay, they'll put all the numbers in a hat or in a box and pick them out, and those are the winners. That means there's 5 winning numbers and 40 losing numbers in the lottery. Okay, so what I want is I'm choosing 5 numbers. The number of possible outcomes is either going to be permutations or combinations, picking 5 numbers out of a possible 45 numbers. That permutation or combination result is my denominator. That's the number of ways all the different outcomes can occur. I want to select out the special winning ones. What's a winning one? 3 of your numbers have to match one of these guys, one of the 5 winning ones from the lottery. Okay? So 3 of my numbers have to be winning numbers. I guess a better way to say this would be, the special outcomes would be, I have 3 of my 5 numbers in my outcome, or let's just say 3 of my numbers match a winner. What's a winner? And there's 5 winners. 5 winning numbers right here. And then the other 2, so that takes care of these guys. The other 2 of my numbers have to match what? A losing number. And how many losing numbers are there? There's 40 losers in this case. Why? Because there's 45 numbers. 5 of them are being declared to be winners by the lottery company, so the other 40 must have been the losers. So I have to pick 3 out of 5, and I have to pick 2 out of 40. So it's an and situation. I have 2 results that have to occur, and it's an and between them. How do I connect these with an and? Remember what and means? And means, if you recall, that you multiply. Okay? So I need to figure out how many ways can I pick 3 numbers out of 3 of my numbers. How many ways can 3 of my numbers match one of these 5 winners that the lottery selected? And, meaning multiply by, how many ways can the other 2 of my numbers match one of these 40 losers? Where'd the 40 losers come from? Because 45 numbers, 5 of them were winning numbers, the other 40 therefore are losing numbers. And so I'm going to multiply because it's an and. That result, this result right here, once I figure all this out, and by the way, when we say 3 out of 5 or 2 out of 40, does the order matter? Okay, and again, the answer is not in this case, because we're not trying to match, like my first one doesn't have to match their first one, my second one doesn't have to match their second one, etc. It's just I have to have a collection of numbers that's in their collection, okay, or at least 3 of my numbers are. All right, so this is giving me essentially the number in my numerator. That's the number of ways for the event to occur. The event is 3 of my numbers match one of the 5 winning numbers. The other 2 of my numbers match one of the 40 losing numbers. And we're connecting that with an and. They both have to happen. That gives me my numerator. The number of ways for any outcome to occur is my denominator. Okay? So that should help you solve this. It's a bit of a complicated problem, but this is probably the best way to break it down. All right? All right, cool. Okay, so number 6 is actually, it's going to turn out to be very similar to number 5. There's 2 categories of, just like in number 5, that we're winning numbers and losing numbers. Here there's red balls, white balls. Okay? And in the previous problem we needed to select 3 from the winners and 2 from the losers. Here we're supposed to select 2 from the reds and 2 from the whites. So it's really a similar problem. 2 from one category and then 2 from a second category. Just like before, we had 3 from the winning category and 2 from the losing category. Same idea. Okay, so step 1 is identify the sample, like the set of outcomes. The set of all outcomes. What do they look like? How many are there? Okay, so what's a typical outcome look like? We're going to select 4 balls, right? There they are. So you put the 4 balls into these boxes, and there you go. Okay? We want 2 reds and 2 whites. But that's the 2 reds and 2 whites, that's the special outcomes that constitute a winner, or the event that we're interested in. In general, I'm just picking any old 4 balls out of that urn. Okay, so how many ways? How many ways can this be done? What's the number of ways? First of all, if I pick a ball and put it into one of these boxes, it's not available again to be chosen. So I'm not replacing it. Okay? It's not saying I'm picking a ball, putting it back, shaking the urn around, and then picking again. That would be replacement. In this case, I'm not replacing the ball. Okay, that means it's either going to be permutations or combinations, because I'm not replacing the ball. If I was replacing the ball, then it would just be 15, 15, 15, 15, multiply it all out, and you'd have your number of ways for all outcomes, okay? But we're not doing that. We're not replacing the ball, okay? So now the question is it permutations or combinations? Okay, I'm selecting 4 things out of a possible 15, right? But is it, does the order matter? So think about whether the order matters or not, okay? All right. Now, the second step is to single out the special sort of event, the outcomes that are declared to be the event we're interested in. So we want to look at the outcomes. We want to identify the outcomes giving us the event that we want. The special outcomes. Okay, so the special outcomes that give us the event. In the last case, we were matching the lottery's numbers. Okay, in this case, the special outcomes giving us the event is going to look like this. We've got to pick 2 red balls and 2 white balls. It doesn't really matter what sequence, but 2 of them have to be red and 2 of them have to be white. Okay, so how many ways can I pick 2 reds from how many reds are available? From 5. I'm sorry, from 10 in my case, right? So I need to pick 2 reds from 10. Does the order matter? Think about whether the order matters or not. Okay, it doesn't matter what sequence you pick the reds. I need to pick 2 whites from how many white balls? Looks like 5. Okay, so this, and again, remember the set of all outcomes, remember the probability of an event is equal to what? The number of ways for the event to occur divided by the number of ways for anything to occur. For any outcome. So notice when I do my initial number of ways, the number of ways for anything to occur, that's giving me my denominator of my probability. Okay? When I figure out the number of ways for my special outcomes to occur, that's giving me my event, my numerator. Okay? And notice both of these have to happen. So it's this and this. So and, if you recall, means multiply. All right, and that should help you out. And if you'll note, when you set this up, you'll end up seeing, look at the formula that you get and compare it to what you got on number 5, and you'll see it's essentially the same problem. We're just naming things differently. Okay, instead of winning balls, losing balls, we've got red balls, white balls. Okay, other than that, it's kind of the same setup. All right, it's really the same problem again. All right, cool. Let's go to number 7. Okay, so problem number 7 is somewhat similar to the previous ones. Step 1, of course, is to identify the set of all outcomes and then figure out how many there are. Okay, so identify the set of all outcomes and then we'll count them. Okay, we'll use a counting method. So what is this? Let's write down what a typical outcome is supposed to look like. It's supposed to look like 3 people. Okay? President, vice president, secretary. Okay, so you got your president, your vice president, your secretary. Now, notice that in this case, if I select like Tom, Jerry, Bob, that's different than Tom, Bob, Jerry. The order matters because each item in my 3-item selection has a special meaning. So the order matters. Also, of course, we're selecting without replacement because you can't use a person twice. They can't play both roles. Okay, so it's without replacement, meaning we have to use permutations or combinations, and the order matters because a different sequence of choices means different roles for the people. Okay, so these are the outcomes. How many are there going to be? It's either going to be permutations or combinations, depending on which one the order gives you the order mattering. Okay, and notice we're picking 3 people out of 30. Okay, now is this going to be the numerator or the denominator of my probability fraction? Okay, I'm going to leave that up to you. You should know that by now. Okay, second step. We have to identify the special outcomes and count them. What do I mean by the special outcomes? The ones that are singled out to represent the event we're interested in. So these are the special outcomes, in other words, the event. Okay, what is the event? The event's going to look like this. So here's your president slot, your vice president slot, and your secretary. And in the president slot, we have to have either Tom or Jerry. In the vice president slot, you have to have Tom or Jerry. And in the secretary slot, you can have anybody else. Doesn't matter. So we'll use a different color. We'll say anybody else. Okay. Now, the number of ways that these special outcomes can happen, that's going to represent what? Either the numerator or the denominator of your probability fraction. I'm not going to tell you which one. Okay. Now, how many ways can this occur? Well, let's think about it. In this case, I'm selecting what? 2 people. I have to pick Tom. There's 2 people to pick, and there's 2 slots. I have to fill 2 slots with either Tom or Jerry. That's only 2 people. So it's 2 slots or 2 available outcomes, and we're going to fill it with 2 people. And does the order matter? Yes, order matters. Okay. So that's going to tell you whether to use a permutation or a combination. Okay, and it's going to be kind of weird because you have the same number, so it's either going to be 2P2 or 2C2, and it's kind of weird when you have the same number in both places. Just remember, like 2P2, if you choose that, is going to be what? 2 factorial. It's the first number factorial divided by the bottom number factorial. Right? Actually, permutations, it's so NPR is what? N factorial over n minus r factorial, right? So it's going to be 2 minus 2 factorial, which would be what? 2 times 1 over Now 0 factorial is defined to be 1. That's going to be 0 factorial. Let's just write this as 2 factorial over 0 factorial. 2 factorial is 2 times 1. 0 factorial is defined to be 1. I just wanted to remind you of that. So this would just be 2. 2 over 1. 2 times 1 is 2, over 1 is 2. Okay? In other words, there's two ways to do this. You can either pick Tom first and then Jerry, or you can pick Jerry first and then Tom. That's why this is working out to be 2. All right? Now, how many ways can this occur? Well, how many other people do you have to choose from? You have one slot, and you're choosing from how many people? From 28 remaining people. Okay? All right, so what's that going to look like? Does the order matter? Well, in this case, you're only picking one person, so if you want to call it order matters, you can, but it's, I guess you could say that, okay? So that's going to be what? 28 P1. You have 28 things with 1 being chosen. Again, what's that going to be? If you compute it, it's going to be 28 factorial over 28 minus 1 factorial, right? Which is what? 28 factorial over 27 factorial. Now you could do that on your calculator, but you should be able to solve that just by hand really fast. What is 28 factorial? I guess I'm running out of room here, but it's 28, 27, 26, 25, all the way down to 1. 27 factorial looks like this. Okay, so these all cancel. You're left with 28. Okay. And then both of these have to occur. You have to have this occurring and you have to have this occurring. So think about how to connect them. Okay, and then think about whether this represents the numerator or the denominator of your probability fraction. Now, if doing permutations or combinations with these weird kind of like the same number twice or having 1 in the second position, if that kind of weirds you out, you could just sort of figure out the number of special outcomes this way. You could just count them. They're actually pretty easy to count. You could avoid all of that permutation combination stuff and just count them. Okay, and I think I put this in the discussion if you check in the discussion board. Okay, but the other way to count them is you could have Tom, Jerry, and then 27 other people. Okay, or 28 other people, 28 others. So there's 28 ways for this to happen. You can have Tom, Jerry, and person A, Tom, Jerry, and person B, Tom, Jerry, person C, etc. There's 28 ways for this to occur. Or you could have Jerry first for president, Tom for vice president, and then any of the 28 others as the secretary. So there's 28 of these guys, 28 ways for this to happen. There's 28 ways for this to happen. So overall, you've got 56 ways, okay? Which is going to be what you get when you multiply these two guys. All right, so if you do it with permutations, you'll get the same result. Or if you just write out your outcomes, because it's kind of weird to compute permutations when you have the same number twice, or if you have a 1 in the second position, it kind of gets a little weird. You could just, in that case, you can just count them out. But in either case, either this analysis or this analysis down here is giving us the number of ways the special outcomes can occur. And then remember, your probability is, I'm not going to tell you how to compute probability at this point, you should know, okay? But you have your two elements that you need. You have your set of all outcomes and a way to count them, and you have your special outcomes and a couple different ways to count them, all right? And then think about how to create your probability fraction, and you should be all done, okay? Fun, 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 right? Let me Google that, hang on. Yep, Google says it's fun. Right, yep, I just checked it. And there we go.